And now we go through Y index, let's call that one X index for the first point, also here X index. Hello and welcome to another ASMR coding video, and today I'm gonna deliver what I promised in my last video, and you might already see this up here. I have the PDF of my last iPad video where I described to you the DBSCAN algorithm and how it works, and we discussed the parameters and also looked at some examples. And because an algorithm is not supposed to be followed by a human, and instead it's supposed to be implemented in code so you can run it again and again with different parameters, we're going to do exactly that in this video. So that's the algorithm, and if you want to know more about it, check out that other video I made. I will link it in the description. So let's get started with coding. So first let's rename this file because currently it's untitled. So that's also DBSCAN. And at first we need to connect to a runtime here. We're again on Google Colab. I'll also link it in the description. And this will initialize a virtual machine somewhere on Google servers for us. So first we need some data to try everything on and to build around. So we'll use sklearn, which has some inbuilt datasets that we can use. And so, from sklearn import datasets, run this, and then get another code cell, and we will save the iris data by getting datasets load. And you see you have loads of different datasets. You have a Boston dataset, you have a dataset about breast cancer, diabetes, digits, and so on. And we have the load iris, so we do that one and we call it. And now let's take a look at the data. Okay, what's the type? Bunch. Interesting. So we have the data, and then we also have some targets. Oh, and then we also get the target names. Okay, but we don't need those. Okay, we don't even want the targets because this is an unsupervised algorithm, but we could use it in the end to compare it if we want to. But first we'll just get the features of the data and save them in X. And now we can get the shape, and we know that we have 150 data points and 4 columns, 4 features per data point that we can use in our algorithm. Okay. Now let's try and implement the algorithm itself. So we have 2 variables, and I think I'll do the whole thing in a class. So we'll define a class. That's not how you do it. You write class, and I'll just call it DBSCAN, and then you define the init method and pass self. Alright, and in that also pass a min samples and an epsilon, which is the distance, and the min samples will be an integer, and the epsilon will be a float because it's just a distance. It can also be a number with a decimal in it. A decimal? No, a decimal point. Whatever. It can be a float. And we'll save those in the class instance by writing self min samples and self epsilon is epsilon. Right, so far so good. And now we also need to write the main algorithm, and I'll revise this later, don't worry if it looks a bit messy. I'll just write whatever I have in mind right now by referring to the algorithm that I showed you at the start. So I'll just call this run clustering. And we also need to pass it the self parameter. And in the algorithm we also of course need to pass it the data. Data features, which will be a numpy array, and for that we need to import numpy as np. Okay, and now we will have a cluster index, which will be 0 at the start for the first cluster. And now we run through the dataset. So for a point in the data features, now that sounds like we go through we'll just call it, I don't know, let's just call it data. We don't have features and targets in here anyways. For point in dataset, we will do the following. We have to check if the point already has a label, and for that we will have an array which will keep the cluster index for each point. So cluster per point will be -1 at the start because they're all noise, and it will have the length of the dataset. So in that one we can now look up if the point has, can I enumerate this? This would be best. If the point already has a cluster. Then we can look up, so if the point already has a label, so if cluster per point of the point index is not equal to -1, so it has been assigned a label, then we want to continue with the for loop and do nothing here. And if not, then we continue with what I'm writing now. So that will be counting the epsilon neighbors. So I'll just write a comment here. Count epsilon neighbors. I need to write a function for that as well. I wonder if I will do it in this class. I think I will do it for now. So we'll call it count neighbors, and oh yeah, it makes sense in this class because we need the epsilon for it, and so we don't need to pass it to the function if we do it in the class, because it can access this self.epsilon over here. So we pass it self, and we also pass it the point index and the data set, which again is the numpy array, and the point index is an integer. And now we will let's think. We need to go through all the points in the data set and see which one is close enough and which one isn't. So we need a counter, or let's just not do count neighbors, let's instead do get neighbors, and then we can just use the length because we'll need the neighbors later on as well. So still we need to go through all of them and then save the neighbors in the list. And I think I will save the neighbor indices instead. And now we go through y index, let's call that one x index for the first point, also here x index, and point y in let's see if this enumerate works at all before I write it in every function, and it doesn't even work. So let's just copy what I did down here. So for x index in, of course here we have called it capital X, and then let's just print the index, x index, and the point x. I mean, that seems to work quite well. That's good. So delete that again, so we know that we're not totally doing the wrong thing down here. Okay, so first we need to check if it's the same point as x, because of course we don't want to count the same point as a neighbor to itself. That would make sense. So if x index is not equal to y index, then we want to check further if it's near enough. So we need the distance, and the distance will be numpy linalg for linear algebra norm of point x minus point y, and if that is closer or equal to distance away as epsilon, then we append to the neighbor indices the y index. And because this is not nice, we will put this in one if statement and not insert this as much. Alright, so we added it to the indices, that's fine. And then at the end we will just return the neighbor indices. Okay, so here where we wanted to count the epsilon neighbors, we can now say if length of, up numpy I need to write self epsilon, because epsilon is not defined. And now if the length of self get neighbors of x index and the data set is smaller, no, is bigger or equal to min samples. So if the point has at least min samples neighbors, then it's a core point. So then we will assign it the cluster index. So x is core point. Let's just reference this here so we don't forget. And this means we will set the cluster per point at the x index to our current cluster index, which at the start is 0. And we also visit all the neighbors. And for that we will also use the getNeighbors function that I've just written. So for neighbor index in self getNeighbors of the x index and the dataset, we will check if the neighbor already has a cluster ID, and if not, we will set it to also the current cluster index. So if cluster per point of the neighbor index is equal to -1, so it doesn't really have an index, then we will set it instead to the cluster index. And if the neighbor is also a core point, then we will also visit all of their neighbors. So let's abstract this away a bit. It's always best to make your code kind of explicit, so I'll write a very simple function to wrap this kind of logic in here. Also, this has to be self-min samples, I just realized. Okay, so is core of self and the x index, which is an integer, and the data set, which is a numpy array, and this will return a boolean. I didn't write what this returns up here, so this will return a list, and I think I need to import this, so from typing import list. Right, just to be clear, writing the types and such is not necessary in Python, but I like to do it now that it's more supported because it reminds myself and other people who read my code what I intended with it, and yeah, makes it easier to use it later on and also maintain it. But Python doesn't check the types, so it's not like a failsafe, it's just to make it more readable, like docstrings and stuff. Okay, so the is core will literally just check this logic here. So we will return this boolean now, because we need to recursively do this visiting of the neighbors, we will also define that one. So we give it the point from which we want to visit the neighbors, and again, that's an integer. The dataset, and also the cluster index, which is an integer. And maybe we have to return something, but I'll think about this. Okay, so take this code and paste it up here. We don't need it indented quite as much. Okay, so if it doesn't have one, we mark it, and then I think it returns automatically. Yeah. So we mark it, and then we check if this one is also a core point. So if self is core of the neighbor index and the dataset, then self visit neighbors of the neighbor index and the dataset and the current cluster index. If this works on the first try, I'm going to be very, very surprised. Okay. And at some point this should terminate, hopefully. So I don't think we return anything, so we write that we return none. Okay, so down here in our main algorithm, we will visit all the neighbors by just calling self visit neighbors on the x index and the dataset and with the current cluster index. Okay, and then down here, if the point is not a core point, then it's supposed to be noise for now, and it might be visited by another core point later, but then it will get that other cluster index, and we don't have to mark it as noise because we mark all the points as noise by default. So I don't think we need this part here. So instead, after we're finished here, we will set the cluster index to one value higher for the next point. And I think this will, of course this will return the cluster per point array or list. So this will return a list. Alright, let's run this, but this will only define the code. So now we have to create an instance of this DBSCAN thing, and we need to define it with some min samples. Now I have no idea of the dataset, so let's just, let's just say 5 and a distance of, I don't even know, 1, and then do DBSCAN instance run clustering on our dataset. So let's just write dataset is x. Oh yeah, there's our error. Okay, point index is not defined. Oh yeah, I renamed this. Why did I forget to change it? X, oh here. So this is X index instead of point index. Alright, rerun the definition and let's run this. Name cluster per point is not defined. Where is it not defined? Oh, in the visit neighbors one. Right, so yeah, I think this makes more sense anyways. So let's save this in the, I think we can remove these helpful comments now because the functions already tell us what is happening. Okay, and now we can access this via the self parameter. Sounds good. Let's try again. I mean that it ran, but let's look at the clustering. I think either the algorithm is wrong or my parameters of min samples and epsilon are not good. Okay, so I think we created 104 clusterings, which is not ideal. So, alright, let's now visualize the clustering so we can see what's going on. And I'll need a plotting library for that. So import matplotlib dot pyplot as plt, and we also need PCA to visualize the 4-dimensional dataset in 2 dimensions. So from sklearn dot decomposition import PCA. Let's see if I can do this without googling. Let's just ignore these parameters. I have no idea if I need them. And then do PCA dot fit transform, maybe, of the dataset X. Wait, if the, maybe that's why I need to say that I want 2 dimensions. Ah, right. So X in 2 dimensions, let's say it the transform data. And now we can do a scatter plot of the transform data. So first column and Y is the second column. Beautiful, that's the k-means data. And now let's say the colors will be, we can do iris data dot target, and that's the original clustering. And we can copy this, and now what the coloring will be our clustering. So if we make this epsilon quite large, like 4, then we see that we get very big clusters. And if we decrease it to 2, for example, then we see that we get smaller clusters as well, like this one here and this one here. There's one more thing. We can try the inbuilt algorithm from sklearn and see if it does something different than ours. So let's do the one. Let's get the one from sklearn clustering. Clustering import DBSCAN. Of course, it's called cluster. Oh, DBSCAN, and then rerun my clustering. Point X is not defined. Right. Interesting that it worked before. Should I be concerned? We need to access this point. Right, so I guess we found the mistake by accident. So now we have one fat cluster. So we need to adjust the epsilon. Now we have 22 clusters, okay. Do the PCA again. That's the original plot, and that's our plot. This looks already way more sensible. Okay, now let's look at the DBSCAN from sklearn. So this will be DBSCAN, and epsilon will also be 0.5, and min samples will be, what have we got it, 4. And then now call fit on the data X, and that should give us the sklearn clustering, and then we can plot that as well. Oh, we need to plot the labels, of course. Oops. That is pretty identical to ours, even if the hyperparameters are not very suited to the iris dataset, but this means that we implemented the algorithm correctly as far as I can tell. So I'll keep it at that. So let's go up again and look at our algorithm that we did in this class here, and yeah, I hope you learned something, and I hope you could learn from my mistakes, and thank you so much for watching, and I'll see you in the next one. Bye!